Welcome, leaders and technologists. Today, we are unpacking one of the most critical topics in modern business transformation, the importance of secure AI. We will explore how to protect your data, secure your AI deployments, and build the trust necessary to drive real business value. Let's get started. Hello everyone, and welcome. To truly harness the capabilities of generative AI, we must first build a fortress around it. What exactly do we mean by secure AI? It is the comprehensive framework used to protect your AI models, your proprietary data, and your system outputs from unauthorized access or manipulation. The basics of this involve extending your existing application security, data encryption, and identity authentication to cover your AI tools. Why is this our main focus today? Because as generative AI is rapidly integrated into our core business workflows, weak security controls can expose sensitive intellectual property, leading to severe compliance violations and reputational damage. How do we prevent this? We start by applying zero-trust principles to every AI interaction. For our deep dive, we must recognize that generative AI fundamentally expands your attack surface. We are no longer just securing servers and databases. We must now secure natural language. Attackers can use plain English to attempt to manipulate the AI, meaning our security posture must evolve to understand and filter these conversational threats. Let's take a look at the flowchart on your screen, which visualizes the evolution of the enterprise attack surface. Historically, our focus was strictly on the left side, traditional IT security. We built firewalls to protect network perimeters and relied on database encryption. But with the introduction of AI, our attack surface expands down the right side, generative AI security. Here, the threats look different. We must implement prompt shielding to evaluate the safety of incoming text, model access controls to ensure only authorized applications can query the engine, and output filtering to prevent the AI from inadvertently leaking restricted information. As a senior leader, you must ensure your security teams are fully resourced to defend this entirely new, AI-specific branch of your enterprise architecture. Moving to slide 2, let's discuss the foundation of our entire AI strategy: trust. Microsoft's documentation is very clear on this. Trustworthy AI does not happen by accident. What is it? It is the standard that dictates our AI systems must be safe, ethical, and reliable. The basics of trustworthy AI rest upon two distinct but interconnected pillars: high-quality data and strong security practices. Why are we so focused on trust? Because trust drives adoption. If your workforce fears that querying an AI model will leak their confidential project details, they simply won't use it. If your customers receive inaccurate, ungrounded information, your brand suffers. How do we build this trust? Through secure AI. Security practices ensure that the data feeding your models remains pristine and untampered with. In our deep dive, we see the symbiotic relationship here. High-quality data prevents the model from hallucinating or exhibiting bias, while robust security prevents the model from leaking that high-quality data to the outside world. You cannot have one without the other. This diagram perfectly illustrates the architectural foundation of trustworthy AI. Notice the two pillars at the bottom: high-quality data on the left and strong security practices on the right. These are the load-bearing columns. They both feed directly upward into the central node of trustworthy AI. If either of those pillars crumbles, if your data is biased, or if your security protocols fail, the entire structure collapses. When those pillars are strong, the trustworthy AI node successfully branches out to deliver your ultimate business goals: widespread user adoption, strict regulatory compliance, and absolute brand protection. Whenever you are pitching an AI initiative to your board, this is the visual you use to prove that security is not an afterthought. It is the enabler of the entire project. On slide 3, we confront the reality of the new threat landscape. What are the specific vulnerabilities inherent to generative AI? The primary threats are prompt injections, jailbreaks, and data leakage. Let's cover the basics. A jailbreak occurs when a user crafts a deceptive natural language prompt designed to trick the AI into bypassing its built-in safety instructions. Why is this so dangerous? Because large language models are fundamentally designed to be helpful and follow instructions. If an attacker hides malicious instructions inside a document, the LLM might execute them. How does this happen? We call this an indirect prompt injection. An attacker hides text on a web page. Your employee asks the AI to summarize that web page. The AI reads the hidden text and is hijacked. Our deep dive brings us to perhaps the most common organizational threat: shadow AI. This occurs when employees bypass secure corporate tools and paste proprietary code or confidential financial data into free, public AI chatbots, inadvertently leaking your enterprise IP to the public domain. Let's walk through the mechanics of an indirect prompt injection attack using this left-to-right flow. It starts with a malicious actor who crafts deceptive text to create an indirect prompt injection. Notice that the attacker doesn't attack your servers. They embed this hidden text in a seemingly harmless PDF or web page. Next, an unsuspecting employee downloads this document and asks your internal, secure enterprise LLM to summarize it. When the LLM reads the document, it also processes the hidden malicious instructions. Because the LLM is trying to be helpful, it executes the hidden command, resulting in the red node on the right, data exfiltration or malicious output. This diagram highlights why securing AI requires advanced tools that inspect not just the user's prompt, but every piece of data the AI consumes during the interaction. To defend against these vulnerabilities, we must establish rigorous technical safeguards. What are the core requirements? They are divided into 3 layers: application security, data security, and identity authentication. The basics are rooted in traditional IT. Application security ensures the software infrastructure is free of vulnerabilities. Data security mandates that your information is encrypted both at rest and in transit. Authentication ensures we know exactly who is asking the AI a question. Why is this critical for generative AI? Because AI is exceptional at searching and summarizing. If your AI is not properly authenticated, a junior employee could ask it to summarize the CEO's private financial forecasts. How do we prevent this? By integrating platforms like Microsoft Entra ID to enforce strict role-based access control, or RBAC. For our deep dive, remember the golden rule of secure AI, least privilege. The AI model itself does not have superuser access. When an employee queries the AI assumes the exact identity and access rights of that specific employee. If the employee cannot see a file, the AI cannot see it either. This access flowchart demonstrates how least privilege works in a secure AI environment. At the top, the employee prompt hits the first gate, Microsoft Entra ID authentication. If verified, the request moves to the AI orchestrator. But the orchestrator doesn't just grab any data. It passes through the role-based access control node. The RBC system looks at the employee's credentials and determines which databases the AI is allowed to search on their behalf. The AI can pull from the public knowledge base and their specific department SharePoint. However, notice the confidential HR files node with the dashed red border. Because this specific employee does not have HR permissions, the RBC system creates an impenetrable wall. The AI is blocked from even knowing those files exist. This visual proves to your stakeholders that AI does not break your existing data governance, it enforces it. How do we operationalize this security? We use Microsoft's proven lifecycle framework: govern, map, measure, and manage. What is this? It is an iterative, risk-focused approach to building and deploying AI securely. Let's cover the basics. Govern establishes your organizational policies, roles, and compliance standards. Map is where you identify and prioritize specific risks, like data leakage or bias. Measure involves systematically evaluating those risks using concrete metrics. Finally, manage is where you deploy technical mitigations, like content filters, and continuously monitor the system. Why do we need this formal framework? Because generative AI is non-deterministic. It evolves. Ad hoc, one-time security testing is completely insufficient. How do we execute it? By integrating the security development lifecycle, conducting thorough threat modeling, and performing AI red teaming. For our deep dive, let's focus on the map and measure phases. During map, dedicated security teams deliberately attack the AI process called red teaming to find vulnerabilities. Then, in measure, we use tools within Azure AI Studio to statistically quantify how well our safety filters blocked those attacks before going to production. Look at the circular flow of the govern, map, measure, manage framework on your screen. We move from left to right, starting with govern, where the rules are written. The flow pushes into map, where we actively hunt for threats using red teaming. Once we map the vulnerabilities, we move to measure, applying rigorous, data-driven safety evaluations. Finally, we land on manage, where we lock down the system with active mitigations and set up live monitoring. But notice the crucial dashed arrow returning from manage back to govern. This represents continuous feedback. AI security is never finished. As models update and adversaries invent new attack vectors, your live monitoring feeds data back to your governance team so they can update policies, restarting the cycle. This is the heartbeat of a mature, secure AI enterprise. Let's apply this to a product you will likely deploy, Microsoft 365 Copilot. What is the security posture here? This is the definition of secure AI within a SaaS environment. The basics rely on a process called grounding. When a user asks Copilot to draft a proposal, Copilot searches Microsoft Graph to find relevant documents. But crucially, Graph strictly enforces permissions. It only retrieves files, emails, and chats that the specific user already has rights to. Why is this architecture so important? Because it allows you to unleash powerful AI assistants across your company without violating tenant isolation or compliance laws. How does it work under the hood? The prompt and the retrieved data are sent to the LLM via encrypted transit, and the processing happens entirely within the Microsoft 365 trust boundary. Now for the most important deep dive for business leaders, Microsoft's explicit guarantee. Your enterprise data, your user prompts, and your generated responses are never used to train Microsoft's foundational models. Your proprietary data remains exclusively yours. This sequence diagram walks us through the exact data flow of a Microsoft 365 Copilot request, proving its security. In Step 1, the user submits a prompt. In Step 2, Copilot routes the request to Microsoft Graph. Graph acts as the security bouncer. It checks the user's RBC credentials. In Step 3, Graph returns only the permitted data. Now, in Step 4, Copilot combines the prompt and the secure data and sends it to the Azure OpenAI LLM inside an encrypted, isolated boundary. In Step 5, the LLM processes the facts and generates a secure response. Finally, in Step 6, the user sees the answer. By visualizing this, we see that the LLM is isolated from the raw database. It only ever sees the specific, pre-approved documents handed to it by the Microsoft Graph, ensuring zero risk of broad data exposure. For organizations building custom AI via Azure, we must go deeper into specialized security layers, Azure AI Content Safety and Prompt Shields. What are these? They are active defense mechanisms designed to detect and mitigate adversarial attacks in real time. The basics involve content filters that analyze every input and output, actively blocking hate speech, violence, and sexual content. Why do we need this if we already have RBC? Because access control only verifies identity. It doesn't verify intent. An authorized user could still try to abuse the AI, or an indirect prompt injection could still hijack it. How do we stop this? We deploy prompt shields. Think of prompt shields as an AI-specific firewall. They use specialized machine learning to scan incoming text specifically for jailbreak signatures, neutralizing the attack before it ever touches the LLM. For our deep dive, we also implement groundedness detection. This system acts as an auditor on the back end, constantly monitoring the AI's responses. If the AI hallucinates or deviates from the provided source documents, the system flags it and can even force a rewrite to guarantee factual accuracy. Let's analyze this defense in-depth architecture. On the far left, we have our input. Immediately, it hits the first checkpoint, the prompt shield. If a jailbreak or injection is detected, the flow branches upward to block request and log, stopping the threat instantly. If the prompt is clean, it proceeds to the Azure OpenAI LLM for processing. But we aren't done. The generated output then hits a second checkpoint, the content safety filter. If the AI has hallucinated or generated toxic content, the flow branches up to flag or rewrite output. Only if the output passes this final inspection does it reach the deliver to user node. This dual-layered shielding protecting both the input and the output is how you confidently deploy custom AI applications into production environments. Let's synthesize everything into a real-world use case that proves the vital importance of secure AI. Imagine a major healthcare network. The problem: nurses are experiencing severe burnout due to the hours spent reading complex clinical charts. The business wants to deploy an AI assistant to instantly summarize these charts. What is the challenge? Patient privacy is governed by strict laws like HIPAA. They absolutely cannot use public AI models, or they risk massive data leakage and fines. How do they solve this? They build a custom AI agent using Azure OpenAI hosted within their own private, secure cloud tenant. They use retrieval augmented generation, or RG, to ground the AI's summaries strictly on their internal, encrypted medical databases. Let's look at the deep dive security posture. They use Microsoft Entra ID, so the AI only ever reads charts for patients assigned to that specific nurse. They deploy prompt shields to prevent any accidental or malicious misuse of the interface. Finally, every single prompt and output is audit logged. Because they built a foundation of secure AI, they successfully reduced nurse burnout while achieving total regulatory compliance. Our final diagram maps out the secure healthcare AI workflow. We start with a nurse logging in, which immediately triggers Entra ID and RBC to establish their exact permissions. When they request a chart summary, the text hits the prompt shield to verify safety. The verified request triggers RAG to securely pull data exclusively from the permitted patient database. This clean data enters the Azure OpenAI model to generate the summary. The output then undergoes a content and grounding check to guarantee no medical hallucinations occurred. Only then is the secure summary delivered. Notice the final step at the bottom. The entire transaction flows into an immutable audit log. This architecture proves to compliance officers, boards of directors, and regulators that generative AI can be deployed safely even in the most high-risk, sensitive industries on Earth. Thank you for joining this session on Secure AI.